Hello, everyone. Thanks for joining our first Warsaw.ai webinar. This time we have to meet only remotely. A few days ago, we decided that this is the only reasonable solution in the current situation, so we hope that you understand. But the good thing is that we are able to invite much more people this time, almost 150. So we hope that you will enjoy our meeting. And this meeting is supported by SAS Poland. Thanks to SAS, we can use the On24 platform for streaming this webinar. Our special thanks go to Agata Zawistowska and Piotr Kramek from SAS, who helped us prepare this webinar. So Agata, Piotr, thank you. And as you have probably heard from our announcement, this meeting is dedicated to applications of AI in medicine. An interesting thing is that we started planning such an event concerning medicine and health a couple of months ago. We knew that it is probably the most important aspect of everyone's life, but we didn't expect that this topic may become so critical just before our event. We hope that you will take the most out of this webinar and that you will enjoy it. The plan for today is as follows. Our first speaker is Aneta Maksymiuk from SAS. She will give a talk titled Using Machine Learning for Medical Diagnosis in Cardiology. The next speaker is Krzysztof Geras from New York University. He will give a talk towards solving breast cancer screening diagnosis with deep learning. And our third speaker, Bartosz Borucki, will give a talk titled Medical Imaging and CNNs for Monitoring of the Achilles tendon healing process. Before I give a voice to Aneta, just one important thing. In this video conference on 24 panel, at the bottom you can write down your questions. The questions will be later displayed by us, by the moderators, by me and Marek. Each lecture will last more or less 20 minutes, and after that there will be about 5 minutes for questions and answers. So maybe we'll be able to extend it a bit, we'll see. So feel free to post your questions during each lecture. All right. So now I'm giving voice to Aneta, our first great speaker.
Okay, thank you. Hi, first of all, thank you for attending even today. Let me do a quick short introduction. My name is Aneta Maksymiuk and I am data scientist and senior analyst in a company that specializes in delivering analytical solutions for business. Personally, I have a broad experience in implementing a variety of analytical algorithms into production in different sectors like telco, retail, manufacturing, finance. And recently I have an great opportunity to use that knowledge in healthcare sector. I would like to share with you a few highlights from a project that was carried out in cooperation with the Institute of Cardiology, the main Polish clinical center of cardiology and cardiosurgery with the highest reference score. So what exactly was the purpose of the analytical project? First of all, creating an engine recommending potential patient diagnosis so that the doctors in the hospital application can complete the documentation faster and better. That means that they do not miss diagnosis because it takes time to fulfill forms. We started from a point where requirements focused on assumption that we know main diagnosis, so recommendations should appear just after a doctor chooses leading disease in hospital application. During analysis, we modified these requirements and decided to assume that we do not know any diagnosis prior to making recommendations. During other presentations, I was asked where is the problem. It's obvious that patient has disease because doctors know what treatment should be proper or adequate. Patient who started his hospitalization can have already confirmed disease, or doctor should run additional tests to confirm hypothesis. But main issue is that there is very little consistent integration of information in whole patient journey. Doctors are responsible for medical documentation, which is usually completed at the end of hospitalization and have many patients. In rush, they often choose to fulfill most important information in sake of time. Big issue is still overusing medical texts like medical notes compared with forms. It's easier to make summary for structured data than from unstructured data. And in medicine, we mostly have to deal with medical notes. During our project, we wanted to choose the right algorithms for recommendations, not only those advanced, but also we wanted to check simple algorithms, which may be effective. I will talk about when discussing ways to generate recommendations. We wanted also to test the potential of data gathered by hospital. It is strictly operational data. It comes from application dedicated different operational areas like drug management, laboratory diagnostics, schedules, and so on. Project was run inspired by agile methodology. That is, we tested what data we can obtain and process as quickly as possible and with valuable project. So what are real benefits of the recommendation engine? Firstly, increase effectiveness of doctors' work, improving the quality of patients and disease data, better planning and financing treatments. Diagnoses are at the basis for settlements with the National Health Fund. What we observed, key benefits may be also convincing medical staff that it's worth to invest in technology and it can truly change everyday processes. We know that machine learning models are excellent, for example, in demand forecasting, and it can be applicable, for example, to drug management. Now I would like to talk a bit about diagnostics and about what we can hear in the context of machine learning and diagnostic generally. Everything depends on how we define research problem. I divided it into two classes of problems. First class, I call it an isolated diagnosis. I refer here to, for example, to image diagnostics, where we analyze scans or certain diagnostic tests and predict whether the patient has specific disease or not, like tuberculosis, cancer, and so on. Similarly, on the basis of ultrasound images, you can build algorithms that determine whether a change in a tissue is malignant or not. Here, the goal is to determine 0-1 if the patient has a certain disease, often based on specific tests. We had a slightly different task. The second class problem, I call it complex diagnosis, assumes that patient can have different disease entities at one point in time, described by different set of information coming from scans, tests, medical notes, and many other data. So, yeah, that was our problem. So, next thing is what we call diagnosis. It's important to say that we have worldwide norm defined by World Health Organization, and it's ICD-10, International Classification of Disease. Issue with that classification is that it's changing in time. ICD-10 has 14,000 codes, and newer version ICD-11 has 55,000 codes. Some of codes are evolving, new codes are being introduced, and it's highly important to choose which ICD version is basing and be prepared to implementing. We should be prepared to implementing changes, because changing classification leads to changing training process for models. In the last 5 years in hospital, there were recognized about 1,800 virus diseases described by a detailed level of hierarchy, and it's about 12% of total available ICD-10 codes. Few words how we generated recommendations. We wanted to start with less complicated methods and compare them with machine learning. So random recommendations were used basically to show how hard it is to guess diagnosis. Expert recommendations are most preferable by medical staff. We all should be prepared that medical environment does not have enough trust in black boxes. Doctors and administration prefer clear messages. we would call it business or medical rules. The issue here is such analysis is rare because only doctors can do it, and very complex, and practically it's impossible to cover all diagnostic codes. So we missed that option because of time. We applied two simple methods based on frequency and basket analysis, and in fact, effectiveness of such methods were higher than we expected. We could simply explain this by the fact that hospital is specialized institute, so variance of diagnosis is relatively low. We compared those simple methods with machine learning techniques, and I would focus on machine learning more in the next slides. When it comes to data, we should consider sources of data in hospital systems, their availability, quality, preprocessing time, memory and disk space needed, and usefulness of data. We had around 2 weeks to prepare data and decided to prioritize data sources. We prepared around 8,000 attributes for hospitalizations, including information about current hospitalization data, historical information about patients, personal information anonymized to age, year of birth, and territory of permanent residence. We had ordered the drugs and drugs taken by patients before hospitalization. Here we also did quite a big job to properly prepare drug information using another categorization, ATC, that is an anatomical therapeutic chemical classification system. We use parameters from laboratory tests and other services performed during hospitalization. What we didn't use were medical notes and scans, mostly because of resources and times. We made an assessment, and it would be useful data, but really needs to, it takes time to prepare it from medical applications. So we resigned from that sources. Quite important issue for recommendation system is a point in time in which we want to generate recommendation and data availability at this point. According to requirements, we train our models, assuming that recommendations should appear in the system closer to the end of hospitalization. We have two scorings. One is independent, and second depends on main diagnosis. Time is here very important, but I don't have simply time to focus on this, so I move on. Data quality is a big big issue here. When we chose our modeling techniques, we considered all pros and cons. So I would like to talk about what can expect when working with medical data. We should be prepared that we have patients with a registered treatment history of completely new, and as rule of thumb, we should treat them separately. So we should have different models. Not all patients undergo the same test of treatments. Many different services we have in hospital systems many different services, procedures, and tests. There were more than 1,000 types of services, different services. We have a lot of missings, so we have sparse matrix, and what's very curious, there is great importance of rare information. So sometimes 3 records is very important for properly determining diagnosis. No randomness, so populations basically consist of targeted patients, specific subpopulation of diseases in case of cardiology. So we have issues with representativeness, hospital patients versus populations versus other hospitals. We have quite a big variability of diagnosis for one patient in time. Some of the diseases may be curable in time, some of them won't. There is possibility to assign up to 20 diagnoses to one hospitalization. Choosing main diagnosis is highly dependable on doctors choosing. We also have different levels of detail of assigned diagnosis, hierarchical structures. So some doctors define diagnosis on higher level of that hierarchy. Some of them choose more detailed diagnosis. We have many diagnostic codes and only around 130 diagnostic codes have acceptable occurrence in history within the history. And also definitions, dictionaries, drugs, guidelines are changing in time. So models should evolving. So we built model based on current state of knowledge, and if we want to retrain models, data and models should be prepared to change in future. And considering all these issues, we chose trees to modeling, mainly gradient boostings and random forests. Okay, so now I want to talk to you a little bit about target. It's how our target looks like. I refer to around 80,000 hospitalizations from the last 5 years. Average diagnosis per hospitalization is around 3. Nearly 1/3 hospitalization has only one diagnosis, so we can assume part of these hospitalizations probably have coexistent diagnosis, but they weren't indicated by the doctor. And how we train models. We cross-checked 4 options. We built individual models for each diagnosis. And we also built one model with multinomial target. And we built models without pure knowledge about main diagnosis and models where we assume we know main diagnosis. And basically, the best results we received training model with multinomial targets, knowing main diagnosis, which is quite obvious. Okay, so what results we achieved? From that experience, we could say that we can achieve very good efficiency by generating somewhere between 5 and 10 recommendations. We checked few parameters like what if we will generate 3, 5, 10, 15, 20 recommendations and measure its effectiveness. So probably it's, for us, it's quite possible to generate around 7, 8 recommendations and still have a very good efficiency. We also convinced medical staff and that we could have a very high efficiency if we use machine learning algorithms in predicting diagnosis. We had 2 KPIs, one on total number of hospitalization where we are right, and the second KPI was how good we are in predicting diagnosis for one hospitalization. So our KPIs for hospitalizations, we have like 87% to 94% efficiency. That means that in such percentage we have of hospitalization, we get at least one diagnosis right. When it comes to patients, so one hospitalization, we guess we guess 70% of true diagnosis. So it's I think that it's not very bad percentage, considering quality of data. Up to also, we discovered that machine learning algorithms have up to 10 percentage point are better, up to 10 percentage point than classic frequency models, and in fact. We were quite surprised that classic frequency models weren't very bad. In fact, models are better when information about main diagnosis is available, and training individual models are less effective than training model with a multinomial target. We also have had some interesting research results and new ideas on the use of advanced algorithms. I want to give you a very short summary about some technicals, what machine we and sources we used. All this project was conducted using SAS via on container, RAM 32 gigabytes, 16 vCPU, disk space 1 terabyte. Our data source were up to 50 gigabytes and training data were like 6 gigabytes. We run codes with models batch, and in fact, as a result, we have models that are prepared to be automatically retrained in the future. So basically, we built a recommendation engine which can be implemented and run after implementation, basically, which now currently is maybe, I would say, in process of doing this. We are in process of doing this. And last few graphs only to show you some interesting thoughts from or insights from project. 10 most common diagnoses is the main diagnosis is hypertension, and it's very common. It's also one of diagnoses that coexist with another diagnosis. So, in fact, if you have hypertension, please check yourself. From models, just to say maybe what's important and what was really interesting for doctors, that it appeared that models shows very good attributes. So age, left ventricular diastole, EGFR, number of units from drugs from certain groups, patient hospitalization, prothrombin index, angioplasty, weight, HDL, also number of days from last hospitalization, and temperature, and much more. We had like 150 most important attributes that were chosen by machine learning techniques. Okay, so it was all I wanted to share with you.
Thank you. Thanks, Aneta, for a very nice presentation. I can see that we have some questions from the audience.
Yeah.
The first question, what is the reasoning behind boosted trees? Is that they are most resilient against missing data?
Not exactly, but for my experience, gradient boostings are great for retraining, if they are properly trained, they are quite stable, and they are more resilient when we have problematic data. So for us, maybe I wasn't clear enough, but when you think about medical data, there are some changing procedures in time. So for example, when we think about drugs, so 5 years ago, and we trained models, from last 5 years, on data from last 5 years, you could say that for specific disease, better were like using occult, and now it's better for doctors. They have like their own recommendations. Now it's another drug, and so data will change in time, and therefore we should retrain the models. And still we have all the data, let's say. And from our experience using gradient boostings, it's easier to retrain them, easier to manage missings, because gradient boostings is quite good at managing missings. Also, they are quite good when we have rare information. Yes, and that we have like only 5% of data valuable for us in some variables.
Mm-hmm. Okay, thank you. The next question, did you collect training data from several hospitals, or was there a single hospital?
It was a single hospital.
Okay. Next question, or two questions which are connected. Yeah. I would like to know if neural networks can help in this, and how about LSTMs and recurrent neural networks?
I would say that we would need more time, because for us we have very short time. We need to show value, and when it comes to neural networks, I would think that it would be valuable, but it should be tested, because neural networks can't like behave badly when we have a lot of missings. And here we don't use data like images. It was data like sparse matrices. So we were afraid that neural networks can be like give us good results, but then on the new data we would have quite a big errors. So I wouldn't say no, but in fact if we would have time, probably we switch to neural networks and compare behavior between two types of algorithms with trees.
All right, and how about the amount of data? Is it sufficient for using neural networks?
It can be problematic. So I think that, okay, so I would say in this data which I used, maybe has little information for neural networks, but in fact we can generate more data, because I know methods to use more attributes and more areas, and to generate more data, and I believe we could prepare some more, of course including different areas. So probably it would be best answer. So now maybe a little, it's not enough, but we could prepare more additional data, and then we could try to check this.
The question, and I will try to combine, merge three questions into one question. The question is about recommendations. Which kind of recommendations are given for doctors? So what exactly was recommended? Because I noted that you said that there might be a multinomial target, knowing the main diagnosis, and you may give, for example, 5-10 recommendations. And also an interesting question is how to measure the efficiency, effectiveness, as you said. And there are two similar questions. You mentioned you achieved 87-94% accuracy. This result was achieved for how many recommendations at one time? And the last question, can you explain 70% results plus how many prediction classes?
Okay. So Paweł, please help me in answering. So I would answer about level. Okay, so when we talk about recommendations, so recommendations is a list, and we were our task was to determine how much recommendations we will show to doctors. So it is list, and on that list there were like 5 recommendations or 10 recommendations on 20 recommendations. So we assume that it's list consisted of 5 records, and in these records we have ICD codes.
All right.
Okay. And second question was?
So the question was about the accuracy. Can you explain the 70% result? And also you mentioned you achieved 87-94% accuracy. So this result was achieved for how many recommendations?
Okay, so basically we these measurements 87-94%. It is calculated for when we recommend 10 recommendations. So if we show 10 recommendations, then we check if within these 10 recommendations we have at least one diagnosis.
Okay.
And if we have at least one, then we counted it like, okay, for this hospitalization, we were right. Yeah. Okay. And when it comes to 70%, I know that's difficult because it's quite fast, but patient can have like one diagnosis, true diagnosis, or can have like 5 of them. So it's not for us it's not right for us only measure how many we get at least one true. So we measured for each hospitalization. For example, for hospitalization A, we have 5 diagnoses that was indicated by the doctor, and we within 10 recommendation we guessed 4. So we were right 4 out of 5. So average for this hospitalization is 70. So basically we in average we we guess or we recommend more than 50% diagnosis in each case. So and I think that this percentage can be better. In fact, we can improve this.
Okay, great.
I do not know if it's like clear.
Yeah, I think that's fair enough.
Okay.
It should be clear. We also record this meeting, so it will be available to all people later on our YouTube channel. So they can also later ask you more questions by email, I guess. Right? And maybe just the last questions. We have some time because we don't have the after party. So we can spend a bit more time on questions. But maybe just the last question from Kasper. Is this system in production? So is it giving recommendations to doctors right now? And also a question from me. Can we use it, for example, to predict that someone is infected by coronavirus, for example, because this is really important nowadays, and the process of diagnosis is very time-consuming.
Okay, so answering first questions, this system is ready to implement into production because all analytical background is ready. So it's really nice, but we have I do not know if you have experience with healthcare sector. It's quite challenging to make that transition into hospitals application because there is integration between analytical results and interfaces in hospital. And it should be done very carefully because we have experienced that it's like psychological issues. So doctors should be eager to use recommendations. So recommendations should be seen like most proper way, and that most proper way or most convenient way, it's quite a big issue to have agreed upon both sides. So the challenging issue here is how to present results that doctors will be eager to use them. So it's not the analytical issue, but more practical and
logical
concern. Yeah.
Okay, I understand. All right.
Yes. Second question, Pavel.
The question of whether we can use it to diagnose coronavirus infection, for example.
In fact, it's quite interesting question because in fact it's new pathogen, and we should have in system some pre-processing that search for similar outbreak in history. And because of this is cardiology hospital, unfortunately, I would say that from last 5 years, within last years, we didn't have such an outbreak. So our models, unfortunately, would be quite unhappily wouldn't be working in such case. Sorry.
Okay, unfortunately. Yeah, but anyway, thank you very much, Aneta, for a very nice presentation, answering questions. We had 9 questions from our audience. So now it's time to move to the next speaker, Professor Krzysztof Geras from New York University. Unfortunately, Krzysztof were not able to come to Warsaw. But he can give a talk from New York. So Krzysztof, I give you a voice.
Yeah, I'm here. Yeah. Hi, everybody.
Hello.
So maybe let me begin. Yes, unfortunately, I couldn't come to Warsaw because of the coronavirus. But since we all moved online, I think it's actually it doesn't make so much of a difference. So. My talk is going to be about something that I worked on for the last few years. It's going to be about how far we already went with deep learning for breast cancer diagnosis and what we could do in the near future. So this work obviously is done with a number of people. With my students and other collaborators who are at the NYU London Health, who are at the CARE Center at NYU Center for Data Science. First, maybe let me begin by stating kind of what is breast cancer screening. So breast cancer screening, and why it is important. So it is important because it's a very common procedure. So in the US alone, about 40 million exams are performed every year. And then 200,000 of the women who go through this process are diagnosed with cancer, and unfortunately, very many of them, approximately 40,000, lose their lives to cancer. So it is not just working on deep learning for this application. It's not just an interesting thing to do from a point of view of machine learning, but it's also potentially very impactful. Now, where this breast cancer screening process is in this breast cancer workflow. So this is the first, screening mammography is the first procedure that someone who is asymptomatic goes through. And then what happens is, if this person shows any, there are multiple possibilities. So if this person doesn't show any kind of, there's no suspicion of cancer, then we can just conclude that this person is healthy and there is nothing else, that there are no extra procedures. If there is some suspicion of cancer, then there are either ultrasound or diagnostic mammography is performed. If these procedures don't exclude cancer, then there is another procedure called MRI that's performed. And finally, if the possibility of cancer isn't excluded after the MRI, then there has to be a biopsy, and then the tissue is sampled from someone's breast. Then the pathologist looks under the microscope, and this is what it looks like. And pathology gives us the final determination of whether this change in the breast that was seen in this imaging process was benign or it was malignant. And I'm just going to be talking about this part. So we are only looking at screening mammography right now. So this first part of this process, and what we are aiming to do is determining whether someone who goes through breast cancer screening has cancer only based on these images. And these are what these images look like when we zoom in a little bit. They are very high resolution, so each of them are at least 2,000 by 3,000 pixels here. There are 4 images that are standards to this procedure. There are 4 images because there are 2 different angles at which you could take an X-ray of the breast, and there are 2 breasts, so that gives the 4 images. Okay, so how we actually formulate it as a machine learning task. It's pretty simple. I'm just showing this for clarity. What we do is we take these 4 images, and then we assume that we push it through some learning model, and then what we want is we want to have a prediction for both breasts, whether there is a malignant change in either of the breasts. And then we also want to have a prediction, kind of like in this case, it's an auxiliary prediction that is helping to learn whether there is a benign change either in the left or the right breast. So you could think of this as even though the benign changes aren't really what we are ultimately interested in detecting, they are helping us learning by regularizing the model. It is a very typical effect of multitask learning. Okay, and obviously now training neural networks is much easier than it used to be even a few years ago. So everybody can download PyTorch or TensorFlow and train some neural networks. Unfortunately, in this case, the situation is more complex for a number of reasons. First of all, there are very few public data sets, and they are very tiny. In our case, we just had no choice but to build our own data set. So we built our own data set of approximately 1 million images that come from NYU. Also, the kind of a more fundamental problem is that medical image data have very different properties than natural images. For example, they are very large and they have very small regions of interest. So we cannot just take resonance 18 and apply it without it being we just can't do it and hope that we'll have amazing results straight away. The data is also multimodal in the sense that we have multiple images, like I have shown a few slides ago, and we have both the image level and pixel level labels. So the image level labels are those labels that indicate whether this image has something benign or malignant, but we also have the labels that for the cases that were benign or malignant, we also have pixel level labels, which are drawn by the radiologist post hoc. So we would like to use them both, and it's not totally obvious how you should do it within kind of existing frameworks. Okay, so I'm not going to go very deeply into our model, but I will just show it here very briefly, which you can then also read about it in the paper, which I will give you a reference at the end. Our model is, we could say, this is a baseline model. It's basically what we thought is going to work reasonably well while using reasonably standard components. So the way it works is we take these 4 images, then we train an additional auxiliary patch level classifier that is using the pixel level labels, and we then apply this extra classifier in a sliding window manner over those original images, which allows us to create those extra input channels. Then we have 4 ResNet networks that process these inputs. Here, the color indicates that the weights are shared between networks. So what it means is that here, this network that processes the LCC view of the breast and RCC view of the breast are shared, and also the networks that process LMLO and RMLO views are shared. So this allows us to reduce the number of parameters in the network, which obviously is always good. Okay, then we have just average pooling, just kind of global average pooling over these representations to create vectors. And then we concatenate these vectors. We have 2 fully connected layers, and finally we have 4 predictions, the ones that I mentioned in this slide showing how we formulate the problem. And then we average corresponding predictions from below. And these correspond to these 4 predictions that I mentioned. Okay, so that works reasonably well. We had, so it's in our test set that gave you a pretty good result, but it's difficult to say what these numbers mean unless we compare them to human performance, and then we can better estimate whether we have done something reasonably well already, or this model is not that useful. So we have done a reader study with 720 exams, meaning that we have actually 1,440 breasts. We have 14 readers, and then radiologists were asked for a prediction of probability of malignancy. And the important thing is here is that the readers are actually, most of them are experienced radiologists, so they should be a strong baseline for our network. Okay. Right. I just saw that there are some questions, but maybe we should discuss these questions at the end. Okay. So in the end, what we are trying to do is we're comparing our network to the readers, but we are just comparing them with respect to these predictions, right? Because radiologists are not predicting presence or absence of benign findings, because this is somehow confusing to them. So we just ask them to make a prediction about malignancy, because this is what they are actually used to in their clinical practice. Okay. So this is how well the radiologists do individually. So you can see that they approach 0.8 AUC in this task when they act alone, which is reasonably strong, given that screening mammography is just the first exam, and sometimes you can't see everything in it. Then our model is actually stronger than individual radiologists, at least in terms of AUC. And that's interesting on its own, but there is more to come. So actually, if we ensemble these radiologists from our reader study, and we simply by taking their predictions and averaging them, then this is still a stronger model than our neural network. However, we can go even further, and we can actually take individual radiologists plus our model, with our model, and if we do that, this kind of hybrid radiologist is actually just almost as good as this big ensemble of 14 radiologists. And this is kind of a practical mode of operation possible. Finally, if we took this ensemble of radiologists and then we averaged these predictions with our model, then we can do even better. So what this is showing you is that there's still some, we can still do better, right? So it's still possible to improve our results. And it's also interesting that, it's very interesting that you can actually, you can even improve these kind of very strong models. Like the ensemble of 14 radiologists is it's a very strong model, and our model is also very strong, and you can still improve it. Okay. And this is showing individual radiologists and an average radiologist in terms of so on the left there's the AUC curve, and on the right the ROC curve is on the left, and on the right there is the precision recall curve, with individual radiologists shown as those thinner lines, and the average reader shown in the thick line. Now, what I want to show you is that when I move to the next slide, you can see that, I don't know how well you can see this, but you should be able to notice that basically almost every radiologist is improved, right? So I will switch a few times so that you can take a look, right? So the average radiologist goes up, but also these individual radiologists all go up, and they actually become much more consistent. Here you can see that there's a little bit of a variance between those weaker radiologists and the strongest ones, but actually our model is bringing them much closer. I think that's a very strong practical result. And the great thing about what we've done, I think, one of my favorite things is that that we put our model and the code online, so you can, everybody can just go there and to GitHub, and you can download our model. You can test it in your hospital if you work at a hospital, or you can just play with it, and it's totally free, just as long as you adhere to the rules of the AGPL license, meaning that you will make public everything that you will produce using that code. So I encourage you to play if you're interested. And there are some example images there, and it's actually this code is actually very self-contained. We worked on it for quite a long time. Okay, so this model I think was pretty interesting, but actually there are the kind of issue of these kind of models is that it is not necessarily trivial to understand what this model has learned without doing something extra. So what we thought about a next step of our work is actually to change this philosophy a little bit and to design the models that explain themselves just through their architecture. And the next model I'm going to talk about is our attempt at that. So we call this globally aware multiple instance classifier. And this model works in the following way. So it's learning only with image level labels. It's not using any kind of pixel level labels. In this first instance, it has a convolutional network which is constrained in such a way that that the last layer of the network is actually in this. Okay, so here when you see where this is set sigmoid, basically this network has a kind of a you could say maybe a bottleneck that produces these two saliency maps, and then there is a pooling function that produces a prediction, right? So this model can only be very accurate if these saliency maps have the right fraction of the pixels either turned on and off. So you can maybe, I can't go very deep into this architecture, but this is these kind of networks that do this kind of something like this are, this process is called wiki supervised localization. This is not a new idea. Obviously, people have been doing this before, but then what we use those saliency maps is quite interesting. What we use them for is quite interesting. So we take a number of these saliency maps, and we extract smaller patches of this image, and then we run additional higher capacity network on these patches. And we integrate representations of these patches with attention network, which gives us this kind of a local prediction. So long story short, what this network so far, the way I explain it is, it's a very good way of learning where to look first with this global module, and then looking at some local details with this local module. And then we also have this extra fusion module that it fuses this local information and global information and makes a final prediction. Okay, I will now show you some examples of prediction of inferences made by this model. So here in this, on the left you have the image with the ground truth, with the pixel level ground truth. Then the second image, the second column are the images, the ground truth images with the patches that are shown that were extracted. Then there is a saliency map for benign changes, and then there's a saliency map for malignant changes. So what you should see here is that actually this model is pretty good in localizing those things indicated by the ground truth segmentation, but it's learning to recognize them without the ground truth segmentation. These segmentations are only for evaluation purposes. Like we didn't use them at all during training. And you can also see that sometimes naturally it is a little bit confused between indicating something as malignant or benign. But this is to be expected. You cannot always perfectly distinguish the benign and malignant changes just in screening mammography. Okay, now here, these are the results, the numerical results. I won't go very deep into them, but what you should notice is that this model is actually very, very accurate, right? It's so if you look at this row that says GMIC ResNet 18 ensemble, it's actually achieving 0.93 AUC. It is more accurate, for example, than our implementations of faster RCNN or DMV CNN. This is the model that I was talking about before. So it's a very accurate model, despite only using image level labels. This model is actually even capable of finding some changes which radiologists consider mammographically occult. That's I think a very interesting property of this model. So here on the left there is this original image, and then The second image from the left is the heat map with malignant changes, and the third from the left is the heat map with. Sorry, first one with benign changes, one is malignant changes, one is with malignant changes, and the kind of important thing about this example is that even though a radiologist was reading this image, discarded that finding that's indicated with red as benign, because this person had some. There were some other reasons to take an ultrasound of this person's breast, and the ultrasound indicated that it is actually a malignant change. So what we found here is just something that radiologists just didn't see. Okay. In conclusion, this model is at least comparable with radiologists in this task as framed in our study. We can improve radiologists if we use our model as a second reader. We can actually even further improve our models and make the results even better. But there's still a lot of room for exciting work that maybe I will talk about some other time. And if you liked what I spoke about, you can look at these papers. They are available online. There's also code for both of these models. Actually, there is code. So I hope you enjoy looking at that. Thank you. Okay, now let me take a look at the questions.
Yes, thank you, Krzysztof. A very nice presentation. Congratulations on some great results. So let's check what are the questions from our audience.
Mm-hmm.
And first question, are there some pre-trained ResNet models for medical imaging?
Mm-hmm.
Is pre-training considered at all for medical imaging?
Yeah, that's okay. Cool. That's an interesting question. So, so it is. So of course you could actually, so you could actually just take a ResNet pre-trained on ImageNet and use it for medical images. We are also doing some form of pre-training that I didn't speak about. So we are pre-training actually on initial diagnosis of doctors as they do screening, and then we do this kind of fine-tuning with the cancer labels. You could definitely do a lot of different kinds of pre-training. So it's unclear to me whether, for example, you would benefit from a pre-training neural network on a totally different medical task. I am not aware of any results showing anything like that, but I expect there's going to be a lot of research on that, and it's a good topic to study.
Mm-hmm. Okay, great. The next question, is the protocol of X-ray taking standardized enough, or did you have to apply some preprocessing to make it usable for machine learning models?
Okay. Well, so it is relatively standardized. The good thing about what we're doing is that even though there are, there are different kinds of peculiarities of the protocol, the machines that are used for taking X-rays are actually fairly standardized. So globally, there are only a few companies that cover most of the market. So these images don't change too much. Of course, we did a little bit of pre-processing to compensate for the fact that the different images were taken with slightly different protocol. They were taken at a slightly different time. It was also taken across many years. So we have to take this into account. But they generally these images relatively seem to be quite similar. Like, it doesn't seem like it's they're fairly standardized. It doesn't seem like this is a problem that will be a major. Doesn't seem like a major problem. Actually, we even heard of from other groups that took our model and applied it to their data, and they were telling us that it actually works very well for their data as well.
Mm-hmm. All right. The next question is about the data set, and there are lots of publicly available DNA sequencing data sets. like RNA-seq, for example, which measure activity in complex of genes, breast cancer, of important genes. Are you planning to add these data sets to improve predictions? Do you have such data for patients?
Okay, so I'm personally not planning to do this, but not because I think it's a bad idea. I think it's probably a very good idea to use these kind of genomics data in in conjunction with radiology data. I just don't have enough energy to do this. But if you're interested in working on that, and if you know how to do it, then maybe you should apply to be my student or or do something like that. Yeah, so I personally, I don't have data like this right now, but I'm almost certain that NYU is gathering this kind of data for many years. So the data definitely exists, but I just didn't do anything about it.
Okay, so I have another question about data. So you said that you have a multimodal data. So what exactly it means? So there are different types of images which you use.
So here, what I mean is that there are 4 standard views, right? So I'm considering these different modalities.
Okay.
So yeah, so it is that's kind of what I understood by multimodality. Of course, there's also a possibility of training simultaneously with, for example, with X-ray and ultrasound, and that's kind of what I'm writing a grant for right now. That would be also a kind of a very obvious next step.
Okay, great. And you also said that you built a data set consisting of 1 million images at New York University. So I guess that probably this data set is not available due to privacy issues, but or maybe it's available similarly to the code.
No, actually, unfortunately, data is not public. It's only, I think it's the only way to get access to it right now is by working with me.
Okay.
But it's possible that perhaps I wouldn't be surprised if other groups, maybe in some other countries where there's less regulation, would soon make this kind of data public. I think that's kind of actually to be expected.
Okay, great. But can you maybe tell us how did you build such large data set? Because maybe we can try to do something similar in Poland, in Warsaw.
Oh, absolutely. Yeah, sure, absolutely. So NYU actually, even though most of you probably have heard of NYU as being a university, NYU actually has a part of NYU is called NYU Langone Health. It's actually a chain of hospitals, and and they've been collecting data for a very, very long time. So they collected all of this data. I used data that they collect over a decade. Then I simply asked them to give me all breast X-rays they have in a period that let's say there's this kind of there's something called IRB protocol that this kind of protocol allowed me to legally access. Then I asked the pathology department to give me those reports that indicate whether someone actually developed cancer. And then I just had to do, I guess I could say that, like a Polish miner, I had to mine that data for a few months. There was a lot of data preprocessing, data cleaning.
Okay.
A lot of understanding of how this data is actually collected, how what are these parameters of acquisition. So it's actually I wrote if you actually look at my paper, you can actually read a technical report that explains this in a great detail, specifically this part on data extraction. I wrote it because I expected that many people will have similar problems because nothing like this is explained anywhere. And I didn't want people to go through the same thing again. So you can read this report and basically do this kind of thing that I did much easier with much less effort than what I had to put into it.
Okay, great, thanks. The next question, how susceptible are the networks to so-called adversarial attacks?
They definitely are. I don't know how susceptible because I didn't try, but I'm sure they are. I think I don't see any reason why they wouldn't be. The good thing is that it's very difficult to inject adversarial data into the hospital system. So it's just, I guess it's not a very practical problem in this context, but you could. I'm almost certain they are susceptible to adversarial attacks.
Okay. Good. Thanks. And the next question about the attention. Attention mechanism for explanation model. Is the attention only applied to the set of extracted patches? If yes, is the spatial information about patches position added somehow to attention mechanism? And have you thought about using non-local attention for both combining information of different modalities and model explanation?
Yeah, so you understood correctly that this is only applied to the set of extracted patches. We are currently not adding the information about the position of where these patches are. I think it would definitely help if you had a good way of doing this. We have done some preliminary experiments with encoding the position, and we were not able to get something significantly better just with such a simple method. But it's definitely possible that you could make it better with something like that. I just wasn't able to get something very easy to work, and I didn't put much effort into doing this. But I think it's a very good project to do. Okay, and the other question is, have you thought about using non-local attention for combining information from different modalities and model explanation? No, no, I have not.
All right. Okay, so maybe that may be a good topic for a postdoc, because someone is asking whether you are currently looking for postdocs.
I'm currently looking for postdocs. Well, if you have your own funding, that I'm definitely looking for a postdoc. I actually was looking for a postdoc, and I think I found a candidate that I would hope I made an offer for a postdoc, so I'm hoping that this candidate will accept it. So I'm not actively looking for a postdoc right now, but if someone wants to make a speculative application with their own funding, for example, with Marie Curie Fellowship, then I'm very happy to host someone like that.
Okay, great for this opportunity. And the last question: how about some interesting research directions in this area? What are the hottest topics, for example? What would you recommend?
Interesting question. Yeah. So I think probably, I think the most interesting, to me at least, the most interesting topic here in this kind of area is understanding whether you can use these kind of models for knowledge discovery. So for example, these models are learning from really massive data sets, right? So they are learning from data which are much bigger than what any human could possibly go through in their lifetime. And we are currently just using them for diagnosis, which is great, which if we can use them effectively, and it makes a difference. But I think the real potential is in actually understanding radiology, or understanding, or other perhaps other medical fields with these models, right? So if we had very good models for very good ways of interpreting what these models have learned, then we could not just make prediction, but we could actually maybe even change medicine, right? And then this is really, I think, this is probably a topic of something that is going to be. This is probably going to be a topic of research for a very long time. And you can see that some of these models are actually discovering something that humans don't see. Like in this example, in this mammographically occult example I've shown you. So there's definitely, there are definitely multiple Nobel Prizes to be won in in there. I think the other kind of interesting topics around this is also learning from different types of imaging exams. So here I'm only talking about X-ray, but then, but there are other imaging exams like maybe ultrasound or MRI. And if we could integrate information from these different imaging exams, then we could maybe discover something that is way beyond human perception, right? Because it's very difficult for a human to integrate information from so many different images, understand how it's related to each other. So maybe if we could access this information, and if we had good models for connecting this information, then we could go way beyond what is possible with like human perception and human understanding. So I would say that I think it's kind of like a superhuman aspect of it. So making models that are superhuman, that have superhuman predictive abilities, and then understanding what they have learned and putting that back into science. I think this is something that I would really like to work on in the future. Okay, great.
Thanks, Krzysztof, for this very interesting and insightful talk and answering questions. All right, so...
Thank you very much.
Thanks. I think that we can move to the last talk. Last but not least, our third speaker is Bartosz Borucki, and yes, we can start slides. All right, we are almost ready. Okay, Bartosz, we can start.
Yeah, so if you can just confirm that you can hear me, it would be great.
Yes, we can hear you.
Great, perfect. So, hi everyone, and I'll be happy to share with you some information on what I've been doing for many years now, and I will talk about medical imaging and neural networks, convolutional neural networks for monitoring of the Achilles tendon healing process, which is a very interesting case from view. But let me start from the very beginning, and Krzysztof already gave you some introduction for that. And a few years ago, it was a very, very popular quote given by this guy that you probably know, that if you work as a radiologist, you're like the coyote in the cartoon and you're already over the edge, but you haven't yet looked down. Today, we know that we disagree with that, and we claim that the radiologists that are not using AI will be replaced by the radiologists using AI, but AI will not replace radiologists. And you have already proof in Krzysztof's talk, as you can see, that the combination of radiologists and AI is working great. So, hitting the radiologist, we've been fighting with a problem of Achilles tendon diagnostics. Why it is important? Because from the medical point of view, orthopedics and sports medicine, actually, it's one of the most common orthopedic injuries, the problems with the Achilles tendon. Actually, only in the US you have 60,000 Achilles tendon ruptures in the US annually, and it's mainly sports related. But if you look a little bit a part of the rupture problem, it is said that it suffer annually the problems related to the Achilles tendon, and it's responsible for up to 50% of all sports injuries, or somehow related to 50% of sports injuries. So it's quite a huge problem in orthopedics. On the other hand, when you look at the state of the art in radiology, the main problem is that there is no systematic scoring criteria for the assessment of the Achilles tendon. It's very subjective, the whole assessment, subjective to the radiologist. The variability of radiological scores is very big. And additionally, the very imaging is not that obvious, as the duality of imaging in musculoskeletal problems and in orthopedics being magnetic resonance imaging on one hand side and ultrasound on the other hand side, it's kind of complementary from the information point of view. So it's not very obvious which modality should be used. So this makes magnetic resonance not that useful in everyday approach. So where is the innovation in what we are doing? Well, first of all, we want to propose a standardized approach for the assessment, and we want to make it structured. We want to make it objective. We want to automate and help the radiologist however we can to shorten the procedure, to make it cheaper, and to make in the screening and monitoring of health in musculoskeletal diagnostics, including the of the treatment process and the rehabilitation process. So our fight with the radiologists started long ago, and I will guide you through the whole path. I will not talk about the final solution, but I will show you every step that we've made to get to the solution that we have right now. So first, let's start with a data set. So this is a very unique data set worldwide, as nobody has ever done such a detailed analysis of the Achilles tendon problems with medical imaging. We have both magnetic resonance and ultrasound data set, but I will not focus on ultrasound in this talk. So let's focus on MRI only. So we've had 30 healthy volunteers with a single study as a reference, and 60 patients that were actually monitored 10 times during the healing process of a ruptured Achilles tendon. So once before the surgery and 9 times after surgery, up to 1 year of healing. So together, ultrasound and MRI gave us up to over 1 million slices. And it's quite nice and big data set. This was a hidden slide, so I will skip ultrasound. Okay, so this is more or less how the MRI data set looks like. We have both axial and sagittal slices, but let's focus on the axial ones, and I will tell you later why. And inside this imaging, in magnetic resonance imaging, you have something like protocols, imaging protocols. In CT, more or less, you get a single image, like you're doing a photograph with grayscale. But in MRI, you get a number of different protocols of imaging showing different physical things that can be measured with magnetic resonance. So you can look at it as, for example, RGB bands in an image, or doing a photograph in different light bands, for example, in infrared or something like that. So we have 10 of them in our data set, and here you can see 8 examples here, and each of them is showing a little bit something different. Additionally to the images that were collected for these 60 patients, 10 studies, so 600 studies, we have manual segmentations of the region of interest, which is the outline of the tendon area, done on each slice in a single study series. And additionally, we have something that we use as labels, which are the radiological surveys. So the survey was something that was designed together with orthopedists and radiologists to propose a standardized assessment of the Achilles tendon. And there are 6 scores that are somehow clinically relevant to the assessment of this problem. And each of them is assessed in a 7-point scale. And I will get back to them later, as you will see the results. So we have this labeling for each study. So monitoring how these labels change in time, you can see what is the progress of healing of each patient. Okay, so as usually in CT or magnetic resonance imaging, what you get is a stack of images. So this is some way of slicing the 3-dimensional space of a patient and creating images. You can do it in different directions, and you can do it with different resolution. And What is most important in 3D imaging in especially magnetic resonance is that the grid of these voxels is very anisotropic. So is much bigger than the resolution of a on a given slice. And in our case, in most protocols, it is 0.3 by 0.3 by 4 millimeters. And this 4 millimeters is quite far compared to this 0.3, which raises a question about interpolation and using this Z direction, this third dimension information with these slices. So do we want to interpolate? 4 millimeters for human body is quite far, especially on tissue morphology. You will get a lot of interpolation artifacts. And on the other hand, if we interpolate it to volumes, we will end up with only 600 volumes, which might be a little bit too low for deep learning solutions. So we don't want to do that. So there's another approach, which is usually called 2.5 dimensional approach, which is usually quite good for applications like segmentation or extraction and analysis of some local features, for example, nodules. Usually, if you take a CT scan of a chest and you are looking for pulmonary nodules, quite often you apply this 2.5 dimensional approach. So you are just taking 3 slices, cutting through a single place in space to assess this single place. Is it a nodule or not? But this approach is not very useful for global assessment, and we want to have a global assessment in our case. So we didn't want to use that approach either. So we are left with 2D. And because we are focusing mainly on the morphological patterns that are inside a tissue, we wanted to take the slices that are compared to the direction of the Achilles tendon. So this was our choice. But this is not lacking the problems. Namely, as I mentioned, we have several protocols. So we are imaging the same Achilles tendon, the same space of a patient with 10 different types of imaging, 10 different protocols. But the problem is that they are not spatially aligned, and they are not spatially aligned in two ways. So first of all, because of the protocol of data acquisition in MRI, the slices does not cover the same space. So it's not like taking a photo and dividing it into red, green, and blue bands, because there is no spatial alignment. So we cannot do it, we would have to interpolate. Sometimes is that if you have this 4 millimeter spacing between slices, another slice in another protocol might hit between the slices, so you get a 2 millimeter shift, for example. Or you get a different number of slices. This is also quite common. So again, a problem with interpolation. And additionally, magnetic resonance imaging takes a lot of time. To gather this data set, a patient has to be inside an MRI machine up to, let's say, 40 minutes, maybe up to 1 hour. So he's moving. So quite often there is a shift of patient inside an MRI machine, so there is a problem with alignment. Well, of course, we can do the three-dimensional registration, but again comes in interpolation. So if we have problem in image space, maybe we can interpolate in space. We don't know, but we've made another decision, and I will get back to that. Another problem is the labeling, which actually brings the problem of weak supervision here, because in the training process, we only have a label per study. So we are not labeling what is the tissue state on each slice. We are labeling the whole study. What is the tissue state of this patient at current time step? So we actually have the same label for all slices. And in fact, the tissue differs along the z-axis. And at the same time, at the inference level, when we are assessing each slice, how can we combine the assessment of each of the slices in the stack to give a global score, having actually different scores along the z-axis. So these are the problems that come with this two-dimensional approach in a three-dimensional world. So we've made some assumptions. So first of all, we don't want to have any interpolation. We want to use axial slices, and we have two levels of weak supervision. Actually, the one weak level is the top level labels, which are actually healthy or injured per the whole study. And additionally, we have these 6 scores assessed by a radiologist, again, per the whole study. So we have a top level and a mid level weak supervision. And after that comes a question, should we or not? And the heavily nonlinear features, for example, introduce some information for our problem. So we've started from this last question, and we started with a classical approach. As you can see, this is already 3 years old, and the tool is called Haralick's features. I don't know if you're aware of that tool, but Haralick features is a classical approach to assess the neighborhood or a bigger area of an image with some textural features. The algorithm is based on the collocation matrix, and we are looking at what are the differences between pixels in different adjacencies. So we're looking actually what are the differences between neighbors. The easiest way to understand Haralick's is that they more or less can differentiate between if something is striped or dotted. Okay, so we can calculate it for the whole slice. We can calculate it for a neighborhood. But what we've done is we've calculated these features for the whole region of interest. And the region of interest was something that I've shown you before, and it was the outline of the Achilles tendon tissue on a single slice. So for each slice, which is our data point, we receive 36 features, which are the 12 Haralick descriptors with 3 different adjacency distances. So we have 36 dimensional feature space. We run it through PCA, and we look if something interesting happens in the most significant principal components in the feature space. And to our surprise, the answer was already yes, that something is visible. First of all, we can see the drift of the patients while they are healing towards the healthy group, and I will show you this on another slide. And a part of that we can see called a healing curves, and you can see it on the graph here. So that there is certain specific pattern of the tendency of how the score of the patient is moving along the time. And actually, what you can see on this graph is just a measure that is a distance in the feature space, the distance of a certain patient in time from the referential healthy population. And this is the animation showing you an example of a certain group of patients that are approaching this. The animation shows you the time, so the farther they are, the more injured they are, and the blue one is the referential healthy group. And as you can see with healing, they are approaching much closer with this simple Haralick features assessed inside the tissue only. But after that, as everybody CNNs in 2016 and 17, we also tried that. And first we started with a question, can we healthy and injured cases with convolutional neural networks? So back then we've trained AlexNet and ResNet 18. These two are hit with just this binary classification problem, and checked what we can achieve. And the accuracy that you can see was above 96% for both networks with the classical output. And if we replace the head of the network, cutting the softmax and putting inside something different, for example, SVM, or something that we call the TUNET which actually was the sum of all the last fully connected layer output, we achieved even bigger accuracy for binary classification between healthy and injured cases. Actually, in this work, focusing only on healthy being the healthy population and injured being the pre-operative and 1 week after surgery cases, not looking at the one healthier and healthier afterward. And this was already presented in 2017 on CARS and NVIDIA GTC. And we've also asked a question in that paper: can we CNN generalize the assessment, having a weak supervision and being trained only on the binary cases, so for healthy and injured? Can we, similarly to heraldic features, can we represent a continuous grade of the healing between injury and a healthy state? It was yes, and the results were quite nice. So again, we reconstructed the curves that were of the same pattern that we have already seen, and that was confirmed clinically, and that the absolute value of this last fully connected layer might be also a health measure, having a network trained only for binary classification, and doing the assessment doing the assessment cases from the whole healing spectrum. Yeah, we've also taken a look if with the GradCam if our network is looking where it should, and this is just one of the examples showing that it's really focusing on the Achilles tendon area, even though we are giving the whole cross section of the foot of the lower limb actually to the network. So the next step was just to go deeper, and these results were already our biggest step as it was presented on MICA in 2018 and also NVIDIA GTC in 2018. This time we have chosen AlexNet, ResNet, and Inception v3, again training them binary for healthy and injured cases, using all the protocols this time, having a larger data set, and of course doing some data augmentation, validating it with five-fold cross-validation. And what we found out that for the binary classification, and as you can see here is the accuracy results, AlexNet and GoogleNet or the Inception performed much better than the ResNet, and we thought that the lower performance of ResNet is its tendency towards the very low-level features. And this was actually the hint for us that we shouldn't focus only on the low-level features like the heraldic tendons and the texture that is very local to the tendon, but we should also focus on something that is going on in the bigger, and we'll get to that. In this work, we've also compared the technology. So we've been comparing Pascal and Volta architectures to check what was the performance of the training. And still, going back to the same question, can we use this CNN trained binary as a feature extractor and do some weekly supervised training? So we've chosen the AlexNet as it was performing quite well, and it's much simpler and faster to train. And we took this time not the last convolutional fully connected layer, sorry, not convolutional, but the last one fully connected layer, but the first one fully connected layer, taking 4,096 features that are the output of this layer in AlexNet. Again, we run it through the principal component analysis. Notice that we have over 50% of variance in the first principal component. So we just took the first principal component as a health measure. For a single slice, of course, because we are still assessing single slices. And yeah, it was a good shot. And then we've aggregated the slices in a single study using just a truncated mean. So as you can see here, using the 2.5 hinges, so we were just dropping out the external results that were, in most cases, it was either the very healthy tissue that was on the end of the study, on the boundaries of the study, or it was a very damaged damaged tissue, and we took this truncated mean as the score for the whole study. And we checked how we correlate to the ground truth, and the ground truth, as I remind you, are the scores assessed by the radiologist. And here you can see a table for these 6 scores and 8 of protocols that we've been testing on this stage. On the basis of this research, we've made a decision to reduce the protocols, and we've only chosen the PD, T1, T2, and T2 star GRE protocols for further work. An additional part of this work was also a 3-dimensional approach for GradCam. We've been actually assessing a single 2-dimensional slice with GradCam and then stacking the saliency maps and looking with isosurface how it behaves in 3D and how does it maps to tendon area. After that, the next step was to ask ourselves the question, okay, it's already working nice, but can we use a little bit more of variance that we have in our data? And does it make a sense? So again, we've taken AlexNet and had trained it binary. This time we had more studies. Again, we took the same 4,000 features as feature extractor. We've run it through the same PCA. But this time we took 10 first principle components having 90% of variance inside. And we selected several regression models to compare whether it helps with this analysis of these 10 principal components. And after that, we have chosen, and a part of that, we have chosen only 3 protocols to analyze, as you can see here, PD, T2 star gradient echo, and T2 star gradient echo with minimum echo time. I will comment on that later. And our measure, which was actually the mean absolute error for each patient, was very, very good. The results that we received were below 1 mean absolute error in the 7-point scoring scale, which is already much lower error than the subjective variance of several radiologists that we have here. But still, we have some parameters that had a huge error, but this was mainly related to the parameters that are not very well visible in the axial slices, and the sagittal slices were working better for that case. Okay, so at this stage, you probably already ask yourself a question: why are you still focusing on this binary classification approach, and why don't you train end-to-end? So you just take an image and exit label, just train it like that. We've done so. So we've done this, let's say, supervised approach, but still remember that the label was for the whole study, not for each slice. So there is some inconsistency in labels, or I would say that there is an error in labeling. We've trained separate network for each of these 6 scores that we were assessing. We've optimized toward the minimum average error, again with the same 3 protocols. And the results you can more or less see in the graphs, but the output was that the mean absolute error that we received was around 1 to 1.5. So it was a little bit worse than what we've shown before in the previous step. But what strongly decreased was the maximum absolute error. So still in the previous approach, we were making maybe not a lot, but some cases with huge mistake. So even up to 3 or 4, which is quite huge in 7-point scale. And in here, our maximum absolute errors really, really significantly reduced compared to this weakly supervised model. And after that, we've came to the point where we asked ourselves the question, can we somehow combine these 2 approaches? So can we use both the deep learning learned features from our convolutional network and the handcrafted features, in this case being our heraldic features, and can we combine? And then this work was already on Mika last year. And what we've done is more or less shown here. So the yellow part is what you've already seen. This is the same feature extractor extracting these 4,096 features, running through the principal component analysis. A part of that, we took our handcrafted heraldic features and some statistical features that were calculated in of interest, and we've run it through the lasso method and meta regression at the very end. And what happened? So, first of all, the training was more or less the same as we already seen, but we took 200 principal component, first 200 principal components, having approximately 99% of variance, and we took 46 features from the region of interest. So again, the 36 features of heraldic and nine intensity statistics features and one the cross-section area geometry. So adding this together, being this 246 features, run it through a lasso method to select which features are really important in our analysis. We've done this with this fourfold cross-validation targeted on optimization of the correlation with the ground truth. And sorry, there is an alpha missing. The result for our lasso method was that we are using the best alpha that we can use is 0.1. And you can see the results in this table, namely how many features were chosen by lasso to the final model, and it differs between these 6 parameters that we are assessing. But as you can see, there are just 4, 5, or 6 features extracted by this convolutional network, and 7 up to 10 handcrafted features. Not always the heraldics are used. More or less, the features selected by the lasso method were always below 20. So having these less than 20 features, we have run it also with the tests of different regression models, and you can see the results in the table actually. So we've been comparing the polynomial, the SVR, linear regression, NPR, and to our baseline from the previous method and from the limited data set baseline, which was our other validation data set. And the result was that we have still decreased the mean absolute error even more. So now it was, in many cases, much lower than 1, even approaching 0.5, 0.3 in some cases. Quite nice correlation results also, much higher than in previous approaches. And we've obtained the best overall results with the SVR model of the regression. And we've noticed also that heraldic features really boost these parameters that are really assessed by a radiologist on the basis of some textural features. So mostly being somehow related to these very morphological features of the tissue, and not of course not the global tissues. So our next step is to just add a UNet network here in this pipeline to also automate this segmentation step, so we don't have to segment these datasets manually. We already have very nice results, but we need to improve it a little bit more. Yeah, and these are the results for ultrasound, but I will not discuss on that today. Yeah, so more or less that's it. So what I want you to take with you from this talk is use your weapon wisely for working with your medical images and for specific diagnosis. So remember that not all images are cats or dogs, even though you can see an X-ray of a cat over here on the slide. But it's even not that obvious if you work with 3D data set in medicine. So this is the main problem source, in my opinion, in medical image analysis. To really know what you're doing with a data set and what happens in your data. Then I claim that the incremental approach that we proposed here, that you've seen here, which was actually our way through these last years, really lets you understand your data better and really lets you understand the problem better. As on each stage of our approach, we've been noticing some new additional thing about the data, about the diagnostic process, about the analysis that we can somehow use later. This weekly supervised approach, is it really advantageous? Even though that you've seen that the end-to-end results are even better for maximum error and quite comparable for average error, I claim that yes, due to two things that are really crucial in medical imaging. So first of all, the labeling is much easier. It really takes a lot of time for radiologists to do very pixel level or slice level labeling, and it takes much less time for study level labeling. Especially in many cases, you can automate that just using some text analytics and digging the text descriptions of the studies. And a part of that, you really get higher data availability with weak supervision. So it's much easier to find data that are weakly supervised than they are labeled on pixel level. And just to let you know that we are already on our commercial path with this solution. We've started a university spin-off company that is called Smarter Diagnostics, and we are trying to bring that solution to market. To propose the objective and automated assessment of the Achilles tendon, to standardize the assessment, and to make these radiological workflows more efficient, less time-consuming, cheaper, and allow much more common utilization of magnetic resonance imaging. Thank you, and I'm happy to answer your questions.
All right, thank you very much, Bartek. I can see that we have one question at the moment. As one may treat a sequence of slices as a grayscale video, the problem presented during presentation might be reinterpreted as a video classification. In this domain, there are popular and extremely efficient classical algorithms, for example, based on optical flow and Fisher vectors, which were only recently surpassed by CNNs. Do you know if this approach was used? If yes, how it differs from your approach based on Harlick features?
Yeah, so...
read the question in the Q&A panel at the bottom.
Yeah, so of course you can treat it like that. And I've seen approaches that were also using recurrent neural networks to analyze the slices as a moving image. But this is actually... I would say that for us, it's not the very crucial time to know the difference between separate slices. As we actually, on the end of the day, from the diagnostic perspective, we don't need to assess each of the slices, as our problem is absolutely global. We just need a global assessment of the state of healing Achilles. So what would be more interesting with the approach you propose would be to treat these 10 time steps that we have as a movie and see how this changes. But then we run again into the problem of alignment between the various time steps and the different and the various data sets. Yeah, so more or less, I would say that it might be interesting. We had some approaches to do that, but we didn't go further with that, so I can't really show you any interesting results.
All right. Thank you very much, Bartek. I don't see any more questions at the moment, and we are also many minutes behind the schedule. So I think that, oh, there's one question probably, just a second. How do you collect the data needed to training?
Okay, that's a very good question, and unfortunately, the answer in this case is that it was a R&D project. As you can see on this slide, even there is a reference. This was a project within the StratecMed program, co-founded by the National Center for Research and Development, and this data set purpose of this project, but not for this diagnostic purpose. Actually, the project was meant to show that the stem cells are useful for the therapy of tendons and ligaments. And what we've created, it was a tool to assess and to show the difference between patients with stem cell therapies and without stem cell therapies, the healing process. I will not spoil you if I tell you that there is no difference. So please be aware of using stem cells that you want, significantly from the point of view of images, but it was the side result. So the data set was specifically designed for this project and specifically collected for this project, and it's absolutely closed, being our competitive advantage also.
All right. Thanks for the explanation. I don't see more questions at the moment, so if anyone else has more questions, you can also just send an email to Bartek. You can see his email contact. So I think that I will thank you once again, Bartek, for this interesting presentation.
Thank you.
Answering questions. And yeah, that was the last talk for today, and at the end I would just give you a few announcements and show several slides. Yes, so first of all, thank you for your attention. Thanks to all participants and to all our speakers. Let's stay in touch on our Facebook group and our mailing list. Please also follow our other channels, fan page and YouTube. And one more important thing, after the end of this webinar, you will receive an email with a survey. We'll link to the survey. So we kindly ask you to fill it in and give us feedback so we can improve. We are always keen to learn and improve. Maybe we'll have some webinars in the future, we'll see. So we are happy to hear your feedback. Yes, and we would like also to thank once again our sponsor and supporter, SAS Poland, for helping organizing this webinar. And we would like to invite you to attend our next meeting in June. If everything goes fine, our sponsor and supporter will be Warsaw.ai, and we hope that we'll meet each other not remotely, but during the on-site meeting and in a good health. So take care of yourself and your family, keep calm, and do what you can to avoid the spread of coronavirus, and we hope that we'll meet again soon. So thank you once again, take care, and bye-bye.